Hello everyone. Let us solve this problem 0 to 1 ln of 1 by x, and it is wrapped inside of a fractional part function. First of all, to start off, I would introduce the fractional part function, although I have done it in many videos. Now, this is called the fractional part function and it is defined as follows. So, x minus of box x simply gives you the fractional part. An example of this would simply be, what is the fractional part of 2.7? Now, this can be written as 2.7, which is my x, minus the box of 2.7, where the box is also known as the ceiling function or the greatest integer function. This simply gives you the greatest integer that is lesser than or equal to the required input. Now, this would give me 2.7 minus 2, and this would give you 0.7. And you can intuitively think of it as the part within 0 to 1. That is the fractional part. The properties are that fractional part is always between 0 and 1. It can be 0, but it can never be 1. Almost like probability, except the possibility that it can never be 1. Okay. Now, if you denote the required integral as I and you see that this kind of integrals, whenever you have a fractional part around such a complex thing which you may not be used to, what you do first of all is you always substitute off the thing inside fractional part. So to start off, what we'll do is we'll set y is equal to ln of 1 by x, which is nothing but minus of ln x. And if you solve this, this gives you ln of x equals minus y, and x would be equal to e to the power minus of y, correct? Now, to transform, we need dx. So differentiate both sides and you should get minus e to the power minus y dy. And for the limits, you can see that when x is 0, y must be minus infinity, right? Because x is 0, y must be infinity. Sorry, not minus infinity, because e to the power minus infinity goes to 0. And when x is 1, y must be 0 because e to the power 0 is 1. Which would mean that if I were to write my integral now in terms of the new variable y, I would simply write in corresponding to 0, I would write infinity, right? Infinity, and corresponding to 1, I would simply write 0. Inside, the entire fractional part has been turned into fractional part of y because that's what we have set. And the dx part, which we also found out, is going to be minus e to the power minus y dy. Now, use the minus to swap the integral limits and you should simply get 0 to infinity e to the power minus y fractional part of y dy. Now, we can always evaluate this kind of integrals by breaking the summation. Now, breaking the integral, pardon me. Now, this integral can be broken into integers. And why we do that? So let me first write down 0 to infinity e to the power minus y and the definition of fractional part, which is y minus of box of y dy. And you know that box of y, which is the greatest integer function, that function behaves like this. If y is between 0 to 1, so say y is between 0 to 1, then box of y would be 0. That is the integer that is less. Then if y is between 1 to 2, then box of y would be 1, and so on it goes. So for if y is in the interval n to n plus 1, where n is an integer, you can already guess that box of y is going to be n, right? And 0 to infinity, since we know that integral limits also add up, we can in theory write it like this: 0 to 1, 1 to 2, 2 to 3, and we can continue this process indefinitely, right? And inside we can simply write our integral. So then what we can do is we can simply write I is equal to summation from n 0 to infinity, and simply write down the integral as n to n plus 1. And inside you simply again just copy down whatever you wrote, y minus box of y. But now box of y is going to be different because y is in the interval n to n plus 1. So box of y is going to be n. And there is a dy. And you have introduced a summation outside because you, first of all, when n is 0, it will be 0 to 1, and then n is 1, it should be 1 to 2. And it's a summation, which means it is going to add up all the integrals. Now, summation n equals to 0 to infinity, and you have n to n plus 1. So you write it like this. So n to n plus 1 e to the power y minus n dy, correct? Now, how do you evaluate this entire summation? First of all, in order to evaluate this, we must be doing the integration first, and only then can we try and do the summation. So first let's do the integration as follows. Now n to n plus 1 e to the power y. So we basically have two different parts. So n to n plus 1, the first integral being y times e to the power minus y dy, and the second integral means n multiplied by n to n plus 1 integral, and I think it's simply e to the power minus y dy, right? So these are the two different integrals that we need to first solve, which are not really that hard. So first of all, let's solve this y into e to the power y dy, the indefinite integral. So how do you solve this? You use the integration by parts, right? So the isolate rule, where exponential is the second function, y is the first function, right? So you get y into integration of e to the power minus y dy minus differentiation of y is 1, integration of e to the power minus y is minus e to the power minus y dy. Once you do this, you get minus y e to the power minus y. The minus and minus becomes a plus, but then again the integration of e to the power minus y will give you minus e to the power minus y plus c. And now if you do it with the limits, so therefore n to n plus 1 y e to the power minus y dy is now simply going to be this thing. Firstly, from n plus 1, so it is going to be minus n plus 1 e to the power of minus n plus 1 minus e to the power of minus of n plus 1 minus now the entire thing but in n, n into e to the power minus n, and then minus e to the power minus n. Let's simplify it down. This is going to be we have got all the pluses and minuses here. So we have n e to the power minus n minus of n plus 1 e to the power minus n plus 1. And then you have plus e to the power n minus e to the power of minus of n plus 1. Okay. And yeah, a few things can be copied down from here, obviously. Like you can copy e to the power minus n here, and you can take it common, and you can find this is equals to n minus. So when you take this common, you get here e to the power minus 1 whole into n plus 1, right? Similarly, here you simply get a 1, and here again you get a minus e to the power minus 1. And let's do it further, one more step. And e to the power minus n, and you just simply write n minus n e inverse minus e inverse plus 1, and then minus e inverse. So this is what you have in total. Okay, this is what you have. Now, in a similar way, you can solve this one. And after solving all of these different things, and it's going to be a messy calculation as well, but that doesn't matter. So I'll leave the other integral calculation to you. But then after that, you simply need to use something along the lines where you're going to use the integral infinite series, which would look something like this: e to the power minus n multiplied by y to the power n or something. Now, this is nothing but a geometric series because here y and e multiplied must be lesser. So what we would get is something like this. So this y is just for example, it would be something like y by e o to the power n, and this is going to be an infinite geometric series, provided, of course, the condition that y is less than e. Now, this would give you 1 upon 1 minus y by e, where y is what you're going to get. So, why did I say that? Now, again, this all of these can be derived from the very simple formulas, that is n equals to 0 to infinity, which is the core of this. This is equal to 1 upon 1 minus x, and this is valid for minus 1 less than x less than 1. Similarly, a similar formula is there for n equals to 1 to infinity n x to the power n. And this can be derived easily by first differentiating and then multiplying x. And this is the formula. And this is also valid for minus 1 less than x less than 1. So these are the two formulas that you're going to use in order to solve this. And once you solve this, you can confirm me in the comments, or you can rightly write down the answer here. The answer for the integral is going to be e minus 2 upon e minus 1. So this is going to be the final answer. Well, this was not a very difficult problem, I would say, but rather a very educational one in order to understand how to split up the integrals. And I just showed a very basic integral derivation here. You can do the same with this one and then simply combine them and use these formulas to find the answer. That is the easy part. And we also learned how to split up integrals, how to use the fractional part function, and how to make them work in integration situations where we have a function which we are not really comfortable with. That should be it for this video. If you did like it and you want to subscribe, please do so. And if you have any comments or any feedback,